It's great to be here finally. Actually, I wanted to see the physical disc, but this doesn't work out, so I have to come back at some point. Today's topic we already had in the previous chat. It's becoming of more and more relevance. This slide deck is a little bit older. Most of the data is based or cut off in September last year. And I wanted to emphasize how important it is that computer science and law enforcement work together to understand what's happening in this, let's say, ecosystem surrounding crypto assets. And if you look into recent news, not so recent actually, here you find a lot of success stories. So for example, this is the infamous takedown of the Silk Road Darknet marketplace by the FBI. And following that model, in particular Europol, but also international collaborations involving the FBI, have continued to take down one darknet marketplace after another. So it's a little bit like a whack-a-mole game. Whenever you take one down, another one appears. But on the other hand, it means that somehow the problem is under control. While it's difficult to go after the individual vendor or perhaps a customer on these darknet marketplaces, taking the marketplace down as a whole is effective, and usually what falls out is a whole database of contact points, also shipping addresses of people purchasing illegal goods on these markets, and then conventional law enforcement can kick in. Sometimes this can take some time, so I think the most recent event was when a exchange hack, so it's not really a darknet marketplace, but was a hack of a cryptocurrency exchange from 2016, was solved only a couple of weeks ago. And so essentially it means that criminals cannot be sure that the loot that they get from these hacks can be cashed out into some form of fiat money because analysis of money flows in these cryptocurrency systems is pretty advanced, and law enforcement is able to do that. So what's also interesting is with the appreciation of the exchange rate, the sheer amount of funds seized here. I mean, we're used to big numbers now, but if you think about $3.6 billion, that's about the amount that Wirecard owed when they collapsed. And Wirecard was kind of a bank or a conglomerate of banks listed in the German DAX index. And this is kind of like two gangsters here apparently have controlled this money equivalent. So it's interesting to see the sheer amount. So if we look at this success story, we can ask, perhaps there's no problem anymore. So there's some kind of equilibrium between threat of enforcement that somehow keeps things at bay. However, new problems are on the horizon. One is illustrated here by this little cartoon. Who knows what is depicted? For whom does this ring a bell? Maybe to make this a little bit interactive, put some suggestions in chat. So I see some resonance from the audience. Yes, Justus, you're an expert. NFT stands for non-fungible token. It's somehow a way, to convince people to pay money for essentially a database entry. And this is apparently a big thing. It's most of these systems are, meanwhile, it's fair to say fraudulent, and clearly nothing is really regulated. So it's certainly not a very good investment. Also, some of the propaganda around it appears pretty serious. I mean, they have reasonably artists involved, and often they don't know what they are engaging in. And so it kind of gets this appearance of seriousness, which is perhaps also needed in order to attract investors to buy non-fungible tokens. So what this points to is that not all problems are solved. Taking down darknet markets is one thing, but we also need to keep educating regulators and law enforcement on these systems. And so I've brought a little bit of material here. I hope we can go through everything. It's a little bit on, let's say, the policy side, but also some technical things. First of all, I want to bring everybody on the same page and give you a very brief introduction into what crypto assets are. Then I'm going to talk about money flow tracing. Then I want to highlight one thing that's emerging and that is not solved yet. These are the so-called decentralized exchanges. And lastly, I'm going to give a brief insight in what some people in our lab are doing in terms of building better tools on the computer science side. All right, let's get into what crypto assets are. It's pretty clear to everyone that everything started with Bitcoin, and let me briefly recall how that works. So Bitcoin is essentially a peer-to-peer network that is known from file sharing, let's say in the 1990s and 2000s, but instead of sharing copyrighted material, you use it to manage a huge Excel table, which essentially contains information about which owner owns how much value of some digital unit of account, which is called Bitcoin. And this Excel sheet is updated in so-called transactions. So if this gentleman over here owns a Bitcoin, and these little t's are kind of accounts, and wants to transfer it to, let's call her Alice on the right-hand side, then he crafts a transaction, signs it with his private key, and then this transaction is appended to the database, this big Excel table that is stored on every individual node of this peer-to-peer network. Yeah? So every node has a full copy of the peer-to-peer network. And now, as many people want to add potentially conflicting transactions, you need a kind of resolution mechanism that's called consensus protocol. And one way to deal with one problem that needs to be solved is essentially that competing requests need to be arbitrated in some kind of a random fashion. And the way this is done is by imposing mathematical puzzles that are moderately hard. So it means even for computers, it's not easy to solve, but it's solvable. So after some point in time, this puzzle is going to be solved, and then the database is updated. There's more involved. So for the unlikely case that two different nodes here, due to network latency, find different new puzzle solutions at the same point in time, there is a rule that essentially decides which of the two forks of the branch should survive. And this is what people study in the so-called consensus protocol. Let's just assume that this runs. Yeah, so it's a database that people can rely on, and it's under the control of everyone, and no single party can kind of interrupt or interfere it. Another thing that's important and that's implemented is some rules about which transactions are valid. Yeah, and this keeps the amount of Bitcoins in circulation small. So for example, if somebody, let's say this gangster here who does not own a Bitcoin wants to make a payment, then this kind of transaction is considered as not valid, and it would not be allowed to be entered into the database. And as a result, we get kind of some scarcity that is absolute by the, if you want, so mathematical expression that's encoded in the rule of the protocol. Yeah, that's all about Bitcoin. Everything else you probably get from the media. When computer scientists look at these systems, they usually want to abstract it in layers because it's a way to easily reduce complexity. And this is my version of the technology stack of cryptocurrency systems. So down at the bottom, you have the peer-to-peer network, which just ensures that every node can communicate with every other node. On top of that runs the so-called consensus protocol, which establishes a unique database state. And what's not in this diagram yet, and I'm going to introduce now, is the so-called database state. So this is the persistence layer, which often in typical applications is at the very bottom. Here we have it somewhere in the middle. We call this a ledger, or this is kind of the database. Some people call it the blockchain. What's important is the data stored in this ledger is then further processed in some kind of state machine. Yeah? So this can be of varying expressiveness, so more or less programmable. Even Bitcoin is programmable with simple scripts, whereas other cryptocurrency systems allow more expressiveness. And then on top of that runs an application. So for example, on Bitcoin, the only reasonable application is payments. You know? And if you have a more expressive state machine, like on the Ethereum system, which is arguably Turing complete, you can think of other applications. So we're going to see one in particular later on. These decentralized exchanges are nothing else than applications here. So who are the principals? Yeah, how are people reflected in the system? In order to do that, I have to distinguish the bottom. Yeah, essentially, these are the entities running the system, and these are the nodes. Yeah, they're identified by addresses on the internet, so IP addresses, and we call them weak identities because, there's no arbiter who says who gets access to how many IP addresses. Yeah, you cannot rely that a person only has one IP address. And what's more interesting is what happens on the application, because that is where value is attached, or the crypto units are attached. This is what I call pseudonyms, and pseudonyms are nothing else than public keys of public key cryptography. And they are also weak identities because with a random number generator, you can generate your own key pair and you can generate many of them. So again, there's no guarantee that one person has only one public key pair or one pseudonym. And also what is a priori not clear is which natural person or company controls which public keys on this database. Yeah, so the first puzzle law enforcement has to solve is essentially find this association. And often this association is difficult to find if you have only one key given because it looks like a random number. However, when you look at transactions over time and the relation between transactions, you get more information that can be used to essentially identify whom to investigate. So this is common to almost all crypto assets, and everything started with Bitcoin, and then there came some variants, and pretty soon there came this Ethereum approach. Ethereum is using some ideas of Bitcoin, improving slightly the consensus protocol, but the biggest breakthrough is essentially this Turing-complete execution environment. And now let's just complete this picture. Michael F. Willis in my group was so nice to paint it and find out all the logos. And there's also a higher principle behind the way they are organized. What you can see here is that everything that's running here on the right-hand side is essentially running on the Ethereum platform. Yeah? So not every logo here belongs to a original cryptocurrency, but some are kind of sub-cryptocurrencies, or as people call it, token systems that are running on these programmable platforms. Yeah? You essentially think of nesting. Yeah? You have one programmable platform on which you program your other cryptocurrency, and that's much easier, as we're going to see, because you don't have to deal with the networking layer anymore, and you don't have to deal with the consensus protocol anymore, and so forth. Then around that, you have so-called Ethereum clones. So it's essentially just other instances of Ethereum. And then you have other systems inspired by Ethereum that also support code accounts, meaning they can run arbitrary code in the execution environment. All right, so this is quite a bit, and it's getting more. I mean, it's far from complete. So what I want to focus about in this talk is essentially moving away from, let's say, Bitcoin and Zcash and Monero. This is Zcash actually. This is Zcoin, emphasizing the increasing importance and popularity of systems running on the Ethereum platform. And so I want to first talk about how we trace money flows and why this is difficult or more difficult in the Ethereum platform than it was on Bitcoin, for example. And in order to understand that, we have to understand the relevance of these token systems, of these sub-cryptocurrencies that are just running on the platform. And I just give you some broad figures here, so you can see that Ethereum alone, so the amount of Ether, that's the unit native to Ethereum in circulation, is substantially smaller than Bitcoin. Yeah, it's still not as popular as Bitcoin. However, on the Ethereum system, they run all these sub-cryptocurrencies. And if you just take the top 15 of those, you're almost at the same size in terms of value or so-called market capitalization as the Ether value. And just to put this into perspective, again, we are talking about huge monetary values. This is the GDP, the gross domestic product of Austria in 2020. So it's about, so it's essentially every person's income in Austria in a whole year. That's the value of all Ether in circulation in September 2021. And just to give you an idea of the magnitudes. All right, so why are there so many token systems? Because it's easy to create them. The platform already does all the difficult parts, and it is designed to be open for extensions in terms of new token systems. So even if you're a complete newbie, you probably start with a Google search query asking how to create an Ethereum token, and even the first hit already gives you an example. So here it gives you a smart contract program that's written in a programming language called Solidity for the so-called minimum viable token. So all you need to do is then you need to go to the section that says how to deploy that. It tells you that you need to download an Ethereum node or not even a node, an Ethereum client, and set up a wallet. You do that. and then you copy the code, maybe just change the amount of tokens you want to bring in circulation and insert your own public key to make yourself the owner or the initial owner of all these tokens. And then you need to spend a small transaction fee. Well, meanwhile, it's not that small anymore. It's a few euros. And you deploy that smart contract, and then you hit OK. And within like 20 seconds, that's the usual confirmation time from the Ethereum network, you are your own central bank. You own your own token system. You only need to find people who are willing to pay money for that. So in simple terms, I'm always saying 1997 because that's the year when I built my first website. 20 years after that, in 2017, it was easier to create a financial instrument than building a website in 1997. Yeah? And so if you reflect on that, you can imagine that where all this, let's say, excitement about so-called decentralized finance comes from, and that it, of course, attracts people who want to make short-term profits. Yeah. So why is tracing money flows difficult? The first thing we already mentioned is we only have identifiers, pseudonyms, long, randomly looking bit strings, not names and addresses. So we don't know who belongs to whom. But even if we know that for some, so let's say we know already from some meta information that this is Alice's account, that this is Bob's account. And now we want, for example, law enforcement wants to see if Alice has made a payment to Bob. Then, of course, they could take the approach of Bitcoin and look at all the transactions on the public Ethereum blockchain and establish this Ether transaction graph. And if you just look at that, not every law enforcement currently is able to do that, simply because not all tools that are typically sold to law enforcement support Ethereum. But if they do, then they get a picture like this. And it seems that Alice and Bob have not interacted with each other. Well, not directly with Ethereum's native currency. But what if we consider the tokens? So what you have to do now is you have to understand the protocols that implement the token systems in order to understand their often custom messages that are also stored on the Ethereum blockchain, and then make sense of that and add these edges to the graph. Fortunately, many of these token systems, in order to be interoperable, are more or less standardized. Yeah, they adhere to the standard to a varying degree, but let's assume we have some tool that can deal with all kinds of this standard, then we can add these edges. Yeah, and now you see that there's different tokens also flowing between these nodes, which we haven't seen previously. And now if you look careful enough, then you see, of course, there's direct payments from Alice to Bob, just not via the same system. So it's switching between different units of account, if you want so. And of course, that's something law enforcement has to do, and they're in the process of adopting these systems now. And what is getting even more complicated is if this node 3 here is not a node controlled by a private public key pair, so meaning by some external person, but if this node itself is controlled by a computer program. So essentially it's a smart contract, and that could be one smart contract that implements a so-called decentralized exchange. So it's an exchange where you can swap units of Ether against any other token that is essentially compatible with the system at some price. So think of it as a typical financial exchange, except that it's not one entity which is somewhere in the real world and perhaps resident in some jurisdiction. It's nothing more than essentially a program running on this distributed computer. And so we call this DEX, decentralized exchange. And so, for example, its decentralized exchange could be instructed to make exactly this payment from Alice to Bob using a particular exchange transaction to the decentralized exchange. So means we need yet another layer for forensics that analyzes the protocols of these popular decentralized exchanges and understands which flows are triggered by inputs and how inputs and outputs are related. And this is what we know. You can do this for, let's say, the well-documented and popular exchanges, perhaps with reverse engineering, but nobody stops you from just building your own payments protocol, building your own exchange that doesn't comply with any standard. And then you have what we call the so-called hidden tokens, and we know almost nothing about this. Part of Michael's dissertation was using symbolic executions, kind of a way of analyzing binary code in order to identify such hidden token systems on Ethereum. But it's really a difficult problem, and it's also difficult to measure this against ground truth. So I think I have highlighted to you what the challenges are in tracing money flows, and where we definitely need computer science research in order to improve the tools that are at disposal for law enforcement. Just to zoom into one other direction, I've already introduced decentralized exchanges, and I think that's a big hot topic. So you want to learn a little bit more about that in particular, because these need to be watched not only for law enforcement who want to resolve crime, but perhaps also for financial authorities or for financial supervisors in order to ensure that the financial market works correctly or fair, to the extent that you call this a financial market, this decentralized financial market. So why are DEXs important? Well, first, more and more of them are coming up. So what you see here is a chart of the newly established exchanges over the years, broken down by CEX, meaning centralized exchange, more or less a regulatable entity with some, let's say, business address, versus DEX, nothing else than a smart contract. And you see that in the past years, and the data for 2021 ends in July, so it's only half of the year, new DEXs are more popular than CEXs. And if you look in terms of the total traded volume converted to US dollars, because of course they are trading many other crypto asset types, then you see that DEXs are catching up. And second, please note that this is a log scale here. So there is now still a, let's say, decimal order of magnitude difference. So DEXs are 10 times smaller than CEXs, or the other way around, 1/10 DEX compared to what's done on CEXs. But what is surprising is, well, what are exchanges for? I mean, most of the exchanges are used to convert into cryptocurrency or cash out from cryptocurrency. And this is something you can't do on DEXs, because DEXs don't have a lag in the conventional financial system. So if you take this into account, that essentially almost all volume is probably in and out of fiat, and this is what is not happening on DEXs by principle, then it's pretty shocking how big DEXs are compared to CEXs. All right, here you also see some examples, and what I want to talk about now is what is interesting, perhaps also from an economics perspective, about DEXs. In order to understand that, we first have to recap a little bit how a conventional exchange works with an order book. So what you see here is the bids and asks of essentially US dollar and Ether on an exchange that converts fiat currency in US dollar into Ether. And so what I have on the x-axis is the price of Ether in US dollar, and I need to adapt this slide almost every time I hold this talk. I think 2,500 is a good proxy right now. And then you can see, for example, that somebody is going to give or is going to buy Ether for like 2,499, and then two others are going to buy Ether if the price was 2,498, and so on. So what we get is kind of the cumulative willingness to pay for new Ether. And then, of course, the ask side does this with higher prices. So people are willing to give us up Ether for higher prices. And this way we have some kind of bid-ask spread here. So there's no trade happening, and that's quite natural. And people usually also look at the mid price, and this is what is quoted. So the price of Ether is now 2,500 US dollars. Everything is fine. Now, if somebody now says, okay, I want to buy some Ether, 3 pieces, so then essentially you get these two you can buy, and then you need to buy one of these 4. So altogether, you can buy 3 Ether at an average price of 2,501.33 cents. You do that, and the exchange will match bid and ask, and essentially carry out the trade. And then these ask parts are going to disappear. So all this moves down, and we have a new mid price. All fine. But this new mid price, along with the fact that the trade has happened, is new information to the market. Yeah, so maybe all other market participants here and there now reconsider their own orders, limit orders, and then update their orders. So that means the whole order book moves a little bit. Yeah, you see this is the important part here. Yeah, so this update of the order book. And this update of the order book creates a lot of communication and also creates a lot of state change. Yeah? And this is something you don't want to store on a public database forever that is replicated on almost every, on thousands, tens of thousands of nodes globally, where essentially every bit you store is very expensive. Yeah? So decentralized exchanges had to innovate in a way by finding a mechanism, a market mechanism, that is comparable to the order book known from conventional exchanges, but does not create this, let's say, memory footprint. And the way they do this is that instead of allowing all bits and asks to be stored individually, the exchange dictates some kind of crude approximation. Yeah? And this is approximated with some kind of function. Yeah? And you already see intentionally here that the approximation is never right, yeah? Because it cannot exactly depict every individual's beliefs about future prices. Yeah? But if people deal with DEXs, then they deal with this compromise. Yeah? And that leads us to this notion of an automated market maker using a constant function. Yeah? So this term constant function market maker has been introduced in particular with decentralized exchanges, and also now gains attraction in conventional finance, because conventional finance has never really thought about this because they didn't have the problem of minimizing memory footprint. Yeah, centralized exchanges just run powerful computers and store everything. So what's the idea of a constant function market maker? Essentially what you say is you define a function that takes the amount of ether in the decentralized exchange and the amount of some other token X. Yeah, and for every pair that is tradable, you essentially have this kind of function, and you define this to be a constant. Yeah, so you can imagine here token X versus ether in this diagram. This is all the math that is happening behind. I mean, for the end user, they usually don't understand what's happening. Yeah, for the end user, a decentralized exchange like Uniswap here looks very simple. Yeah, you just have this reduced form user interface where you enter what you want to swap and you get your price, and you can carry out the trade. All right, so let's study a little bit how that works here on the left-hand side. So why does this constant function give us a, let's say, a real market reaction? Well, the thing is the following: assume at t0, the market is at this point. Yeah, so the function evaluates here. So it means we have like about 1 ether in this decentralized exchange and some not further specified amount of token. So now somebody wants to take out token and wants to take out token and pay in ether. Yeah, so he uses some amount of ether. Yeah, it's less than 1 ether if you look at the units here, in order to get let's say x, lowercase x token. And then after carrying out this trade, the market is in this position T1. Now, if the next user wants to buy another X of token, then we start from here. And what you already see from the curvature is that for the next amount or same unit of token, he has to pay way more ether. Yeah, now it's more than 1 ether. Yeah, so what you see is that this constant function gives you kind of a mechanism that updates the price of the token according to demand. Of course, this is amplified. Yeah, I made it big here so that you see the price change in practice. You don't have only 1, 2, 3, 4 ether in a DEX. Yeah, you have many. So there's a role of a so-called liquidity provider who are happy to borrow the ether to these decentralized exchanges, and this scales all this down. Yeah, so now I'm saying 1,000 up to 4,000 ether, and all these little changes are much smaller, and that also means that the market price reaction to trades is smaller. Yeah. So this is more the realistic setup. But let's go back to, let's say, the easy setup, because then we can see what's happening. Of course, these liquidity providers also want to make some profit for borrowing ether to and also token to the exchange. And so they receive a fee from every trade, and this fee is just added here to the amount of Ether paid from the trades. And then there's many more mechanisms going on. So for example, the operator may have a say, but often the operator wants to kind of distribute control in order to not be accountable of what's happening on this exchange. So then they have introduced another sort of token that's called governance token. You can think of it as like a share that not only gives you a profit share, but also some voting rights about policies which trade pairs should be offered on that exchange. So it's getting complex here, and all this is encoded in these programs. So I think that gives you an idea of how these automated market makers work. And now what I want to talk about is about a potential risk that is hard to avoid. And it's also interesting to look at from, let's say, a financial regulation and perhaps even law enforcement point of view. And that is that users of these decentralized exchanges are vulnerable to front running. And let me just illustrate why this is a problem. So when a transaction is about to be stored in the public blockchain, then before it's actually written there or confirmed there, others can see it. It's all public on the peer-to-peer network. And this means others can react to it and as a result, perhaps front run a trade. So let me show how this works. So suppose you want to make a trade here on a decentralized exchange. Then the user essentially defines one of these, let's call it vectors. And so essentially the Y part says how much you're willing to pay in Ether for, let's say, one token X. And now the user has to send this transaction to the peer-to-peer network at a time when he doesn't know whether at the time when the transaction will be recorded, the decentralized exchange is in position T0 or below or underneath. So he has to give a little bit of room in order to make sure that even if the internal state of the decentralized exchange changes a bit, the transaction will still be processed. So what, for example, if it was processed here at T0, then the user would overpay or essentially would provide too much. And the transaction would be carried out until the user pays exactly this amount. So now suppose we are in T0 and an attacker observes this offer of the user. So what he can do is he can craft a transaction that moves the internal state of the decentralized exchange to the starting point where the user would just be willing to engage in the trade. So essentially he takes away the consumer surplus of the user. And we call this a front running transaction, because it's inserted just before the user's transaction. Then comes the victim transaction. So that's the user who becomes victim to front running. And now, of course, in order to make sure that the front running also pays off, also the attacker doesn't want to end up in token, he wants to end up in Ether, assume this is more liquid than token, then he essentially settles this by selling back part of the token he got in excess and receives some Ether. This looks like normal front running on conventional exchanges, which is of course forbidden, and financial authorities are trying to investigate front running cases. Here, there's nobody watching. However, front running in conventional exchanges always comes with a risk, because it could be that something else is happening in between, and for example, that the front runner cannot settle. Interestingly, in cryptocurrencies, in crypto asset systems, this risk can be removed. Because what the attacker does is he does not do these three transactions individually, but he writes a program, a smart contract, that carries out these three transactions atomically. So that means either they are all carried out or not at all. And then the attacker needs to incentivize a miner to, actually put the whole package into the system, because otherwise another front-running attacker could perhaps exploit the opportunity. And this is done with some bribe to the miner. Yeah, we put this as a as a salad you leave here onto the sandwich. So some part of the front runner's gain is essentially offered as a bribe to the miner or transferred directly to the miner or left for the miner to be taken. And this incentivizes the miner to, take this sandwich of transaction and put it into onto the blockchain. Yeah, essentially the miner benefits from supporting this front running. Of course, that's a problem. Yeah, and this can be measured. These patterns are very visible. So there was I think it was a bachelor thesis, but maybe master thesis at ETH Zurich last year, where they tried to estimate the amount of front running gains on a number of decentralized exchanges in just a few months here. It was just over a year. And they came up to like accumulated profits in Ether. Yeah, so that's 60K Ether. That's in the order of 60 million if we just assume a conservative $1,000 per Ether exchange rate. Yeah, so there's a lot of consumer benefit essentially taken by the front running bots. All right, so now I think you got an idea of what's perhaps going wrong in these systems, why law enforcement and financial supervision should watch, and in particular, of course, we also need new laws, but laws are toothless if they're not enforced. Yeah, so we always need to think about how laws can be enforced, and sometimes laws may already exist, and it's just about enforcing them better, and that requires tools. Yeah, because all this is happening more or less in computer programs that run publicly visible, but in some obscure fashion. Yeah, because it's not always super clear. I mean, the whole encoding is very compact. Everything contains cryptographic randomness. I mean, it's not really encrypted, but at least let's call it obscure, right? So what you need is tools, and also these tools have to deal with a huge amount of data. Let me just give you a few numbers. So we have, meanwhile, on the Ethereum blockchain, I think that was summer last year, almost 13 million blocks, almost 1.2 billion transactions, 185 million accounts, meaning more or less identities or pseudonyms on the system, of which 45 million are code accounts. Yeah, these are programs which in principle we have to pass through program analysis, for example, symbolic execution, to understand or at least classify what they're doing. Every day, 100 unique programs are used. Yeah? So also these programs can call other programs, and so it's really complicated to analyze. And this is the total system state in archive configurations in the order of 8 terabyte. Probably now it's 10. So you see, this is nothing you can do on your laptop easily. Yeah? So what you need is some specialized database or special domain-specific database. And this is what Michael also developed as part of one of our Austrian government-funded projects. We call it EtherSci. And the general idea is, and I don't want to go into too much detail, that we essentially unroll and replace almost all of the cryptographic identifiers with integer indexes, and then map all this to large, in particular, fixed size records, which can then be used like an in-memory database. And so this is his architecture here. It differentiates between fixed size and variable size records, and then uses some other standard database to have indexes which allow fast access. So you have kind of an online analytical or interactive analytical access to Ethereum, and of course to some tools that you then run on particular binaries in the system. So here he has some examples of how the interface looks like. So there's a notebook interface. The whole thing is built in Rust. And there's also a web interface and a command line interface using JSON as the data standard. Here's a simple session. So here, for example, he tried to evaluate the gas limit in orange and the actual gas use over time. And I mean, these are the things you extract more or less from the block headers, but it gets more involved when you, for example, look at transactions that are specific to particular code accounts. That's all to give you an idea. I think maybe I'm even over time. I don't know what the intended time was for the talk alone. If you're interested in these and similar topics, we're also looking in central bank digital currency. We are looking into cyber risk, in particular also risk and insurance of crypto assets. And I'm also involved in the first international workshop on crypto asset analytics, not because I'm fascinated of crypto assets, but because I'm interested in solutions for regulators, or how can these systems be watched in a sustainable basis. And thank you for your attention, and I'm looking forward to your questions. And also let me briefly use this opportunity to thank the contributors to this talk, Svetlana and Michael in my group, who prepared some of the material